that finish up chapter 13 and then introduce you to vector functions in chapter 14 before we go ahead any further. Okay. So we ask you to find a distance between these two lines. Now, the first little subtle trick you got to be careful of here is notice here's the component x equals 1 minus t. This is not y alone, the second component, right? So be careful with that. So y equals, it would be t minus 3 over 3. And you get that by solving for y. If you want, you can write that as 1/3 t minus 1. Okay, so there we go. And then lastly, you have z equals -1 minus 5t. All right. There we go. Now, over here we got another line. This is line 1 now, and its parameterization is x, y, and z are all solved for. Here's line 2. X equals -1 plus 2s. Y equals 2 minus s. And then here, we're going to have z equals, and we just move that 4 over, s plus 4. Okay. So now you have your two equations of your lines. All right. The key to getting this question right is understanding the following idea. You need to think of these two lines, line 1 and line 2, as lying in two parallel planes. Okay? That's what you need to do. You need to have that realization, that these two lines are lying in two parallel planes. Okay? It's sort of easy to visualize if you thought about, here's an easy thing to visualize. Suppose you have x, y, z, right? Suppose you're going to consider the xy plane down here, and I had a line in there, this line here. Suppose this green line is in the xy plane, right? So then, if we had another plane up here, parallel to the xy plane, right? And I'll use the color red. The red line's in there. Now, I should be careful about how I draw this. The red line might be going like in this direction. We think about these two lines for a moment, the red line and the green line. They're what we call skew. They're skew. They'll never intersect because they're in two parallel planes that never intersect, right? But they're not going in the same direction either. So we wouldn't call these lines parallel. We just say they're skew lines. Right? So what I'm showing you is, hey, we can draw two planes, put two lines in them, and then we'd agree that these two lines lie in parallel planes. I'm sort of asking you to think about this a little bit backwards. I'm saying, hey, if you have any two lines, then if you're creative enough, you should be able to visualize a plane, two planes. One contains line 1, one contains line 2, and those planes are parallel. Sort of like you can go backwards. You can start with the lines and figure out what the planes look like. All right. Once you have that realization, then you're actually in really good shape because you know the normal vector to either one of the planes that are parallel and contain lines 1 and 2, respectively. Okay? So the normal vector, the common normal, is going to be the direction vector of line 1 crossed with the direction vector of line 2. I know that because of the following. Line 1 lies in plane 1, we'll say. And line 2 lies in plane 2. Plane 1 and plane 2 are parallel, right? The direction vector of line 1, okay, would keep the line in plane 1. The direction vector of line 2 would keep the line in plane 2. Therefore, if I cross those two vectors, I would get a vector perpendicular to both planes. So that's what we're going to start with. So what is V1? Well, V1 is the direction vector of line 1, which has components, -1, you can see that right here, 1/3, and -5. Cross, V2 has a direction vector, 2, -1, 1. So if I cross those, I'll get the normal vector to either plane. Okay, so that's what we're going to do next. All right, so cross products. Here we go. We got I, J, K, -1, 1/3, -5, 2, -1, 1. I put commas in there for some reason. All right, so let's work this out. All right, so watch me on the math here. Let's make sure I don't make a silly mistake. I times its minor. So 1/3, -5, -1, 1. Minus, oops, give me a second there. Minus j times its minor, which would be -1, 2, -5, 1. Just in case you're forgetting your minors, here you are. There's the minor of j. Cross out that column and row. Okay. Plus k times -1, 1/3, 2, -1. Okay, we've done plenty of cross products. So here we go. Here comes our vector. It's going to be our normal vector. All right, so it's going to be 1/3 -5, really, comma. This is going to be the negative of -1 minus -10. And then lastly, we're going to have 1 minus 2/3. Let's sort of finish this up, right? This 5 I could think of as 15/3, I guess. So that's going to be -14/3. All right. Over here, you're going to have -1 plus 10, which would be +9. Then it gets negated, so you get -9. And then 1 minus, I think that was 2/3, gives you 1/3. Okay, great. So that's the normal vector to either plane. And here's my plan. I'm very close to finding the equation of either of the two planes. Plane 1 contains line 1, plane 2 contains line 2. I can find the equation of either plane. Once I do that, I can go for a point on the other line, and I can use my distance point to plane formula. That was how we discussed it. It is not the only way. You can do something with projections also. Okay. So let's do that. Let's find plane 1. Plane 1, which contains line 1. So let's let t equal 0 in line 1, and that implies, what's the point we get? Let's go back and look. We plug t equals 0 in here. We put zeros here, here, and here. We would get 1, -1, -1. Okay? So we get 1, -1, -1, which is a point on L1, and consequently, it's also on plane 1, and that's what I care about more. All right. Now, all we need to do is go back and recall our equation of a plane. Right? Okay. So here's our equation. It's a times x minus x sub 0 plus b times y minus y sub 0 plus c times z minus z sub 0 is equal to 0. Remember, the equation of a plane is a dot product between the normal vector, whose components are a, b, and c, and these other vectors, all stemming from a single point, all have their tail at a single point, right? And we're making that dot product equal to 0 to guarantee that all these vectors are lying in the same plane. They're all perpendicular to the same normal vector, and hence you span out that one plane. So let's finish this up. A, B, and C be the normal vector to the plane, which we have here. That's the normal vector to either plane. Doesn't matter. All right, so it's -14/3 x minus something minus 9 times y minus something plus, I think it was what? 1/3. 1/3 times z minus something equals 0. Okay. Well, I just wanted to go through a point. I already have the point. There it is. So I can just plug that in. So I get 1 plus 1 and plus 1. So here's the equation of our plane. All right, so let's keep our goal in mind here. We're trying to use that distance point to plane formula. We need a point on line 2. So for a point on line 2, I would let s equal 0. If we do that, s equals 0, what do you get? Well, you would get, here, put 0 here, here, and there. You're going to get -1, 2, and 4. So there we go. We got -1, 2, 4. And we're ready to use our distance point to plane formula, okay, which basically says you take this point, you sub it into the equation of your plane, You take the absolute value of that answer and you divide it by the norm of the normal vector to that plane. Okay? So what are we going to do here? We're going to have the following. Absolute value of negative 14 thirds times negative 1 minus 1 minus 9 times 2 plus 1 plus a third times 4 plus 1 over the norm of the normal vector, which would be this expression. 14 thirds, negative 14 thirds squared plus negative 9 squared plus 1/3 squared. Okay? If you went looking at your textbook or online for the formula points of plane, it's usually written ax plus by plus cz plus d equals 0. D is actually present here in the following way. You could multiply that together, and that together. That would combine into one constant, which we would call D. Okay, I didn't bother to simplify it because it would give you the same thing anyway. All right, so whatever this turns out to be is the answer to that problem. All right, so for those interested, the general formula point of plane is ax plus by plus cz plus d, absolute value, over the norm of the normal vector, or this. Okay? And I should be careful. I should say x1, y1, z1, where x1, y1, and z1 are a point not on the plane. Okay? That's what I should be careful. That's the distance from x1, y1, z1 to the plane, whose equation is ax plus by plus cz plus d equals 0. Okay? All right. So let's pretend for a moment that we're given 2 points, like 1, 2, 3, and then another point like 4, negative 7, 5. And you're asked to find the equation of the plane equidistant from these 2 points. Sort of a fun little problem to think about. Now, this question is actually based on sort of like a kind of a common locus question you'd ask in a 2D world. So just go back to the 2D world for a minute. At some point in your past, you saw things like this. They'd give you an xy axis, and they'd give you two points. Let's make it easy for ourselves. Let's pretend one of the points is going to be 1, 2, and the other point is going to be 3, 2. Okay? And the question is, find the equation of the set of points that are equidistant from these 2 given points. Right? So you sort of know right away where you can go. You know you can go to 2, 2. If I was standing on 2, 2, the distance from 2, 2 to 1, 2 is the same as the distance from 2, 2 to 3, 2. Right? And then if you give it a little bit of thought, you could actually go up here too. Any of these points. And why is that? Well, think about it for a minute. Think about it like little Pythagorean theorems. Right? Look at those 2 triangles I just drew. Well, they have the same base, both of them have a base of 1, and they both have a height of 1, so the hypotenuses would have to be the same. And then that would be true for any pair of right triangles you drew, right? You get all these right triangles that were the same. Right? Okay. Well, here's where things change a little bit. If I say, hey, we're going to move up to the 3D world, then those right triangles that I drew don't just lie in a plane, actually. They could span out in any direction off the page, sort of fan around, almost not unlike when you did volumes by revolution, right? In that sense, in terms of visualizing it. But the points that would be equidistant would all lie on a plane that would go through this line and be perpendicular to the board that I'm drawing them on. So the plane would come up out of the board, perpendicular to it, and this is where the plane would intersect the board. So this is sort of like a 3D locus problem, is what it is. All right, I just thought it would be fun for you to realize, hey, wait, I could do that. All right, well, if you have 2 points, you can get a vector. All right, so I'm going to call the vector n. You'll see why in a little bit, by finding the differences in the coordinates. So if this is A and B, well, I won't even do it that way. We'll just subtract it. I'll do 4 minus 1, and I'll get 3. I'll do negative 7 minus 2, I'll get negative 9. And 5 minus 3, and I'll get 2. So this is a vector that is created by subtracting the 2 points. Right? If we drew a picture like this, if you imagine temporarily these 2 points were floating directly above and below each other in space here, then the plane looks like this. The vector that goes like that is actually the normal vector to the plane. So we're halfway there, right? That's what we just did. We found the normal vector to the plane that we're interested in by subtracting the coordinates of the 2 points. So that's part of our equation of our plane. We can start to write it right now if we wanted to. We could say it's 3 times x minus something minus 9 times y minus something plus 2 times z minus something equals 0. Okay. Well, the something now is this point we're interested in. But if we're equidistant from both points, you're going to get the midpoint, which means this is the midpoint of the line segment connecting this point and this point, which we can get by averaging the x values, the y values, and the z values. So if we go up here temporarily, right, midpoint equals, okay, here we go, 4 plus 1 is 5 over 2, so 5 halves. And then you have negative 7 plus 2 is negative 5 divided by 2, so negative 5 halves. And then 5 plus 3 is 8 over 2 is 4. So this is the midpoint. We know that's the point, 1 point that's on our plane that we're interested in. So we're done now. We can plug that in. So we'll get 5 halves here, negative 5 halves there, which makes that plus 5 halves, and then 4. And that's the answer to your question. That's the equation of the plane. It's equidistant from those 2 given points. On to things. Now, let's switch gears a little bit. Let's go to some vector functions. Here's the problem. You've got some vector function, and it's asking you to find the domain of this thing. All right. Well, the domain of this is the following. We have to find values of the parameter t that will make every one of these expressions, all 3 of them, defined. Okay? So for the first one, you're taking the square root of pi minus t. If that's going to be defined, then pi minus t has to be greater than or equal to 0. Okay? So what does that tell me about t? T has to be less than or equal to pi. If t is less than or equal to pi, then when I did pi minus that, I'd get something that's greater or equal to 0. So this is sort of, you can think of as like the domain of the first component. Okay? Now that doesn't actually work for the other functions. Now this second function you can't really see very well, but it's supposed to say 2 to the t minus 1 over t. Doesn't really matter what the numerator says. I just know that t can't be 0. Everything else is going to be fine. Okay? And then the last case, you have the ln, the natural log of t plus 1. You can't take the natural log of 0. You can't take the natural log of anything negative. So you know that t plus 1 has to be greater than 0. That would happen if t was greater than negative 1. Okay? So now I just need to carefully write down the t values that would satisfy all 3 of these things simultaneously. Right? Alright, so carefully writing this down. What can we say? We can start at negative 1. We can't include negative 1. Now, as we move forward, we move to the right along the number line, we get to 0, and 0 is not allowed to be included. So I'm going to do this. Anything between negative 1 and 0 is okay, because it satisfies this inequality, this statement, and it also satisfies that, because all those numbers are less than or equal to pi. Now, I can do a little bit better. I can go a little bit higher. I can also go from 0 up to pi and include pi. Pi is allowed to be included. 0 cannot because of the middle statement. And t being greater than negative 1, well, all of these numbers from 0 to pi are greater than this. So this is the domain for this vector function. Okay, it's the intersection of the 3 domains. All right? All right. Next question. We're supposed to take a look at this vector function and ask the question, what's the limit as t goes to 0? So this is just a fancy way of asking for 3 separate limit problems at once. If we put t equals 0 in the first expression, we just get square root pi. That's not so bad. We put t equals 0 in the second expression, it's going to be undefined. We know we can't do that. However, the limit as t goes to 0 of a to the t minus 1 over t, let a be greater than 0, that's important, is equal to the ln of a. Okay? I'm not saying why, but it just is. So this is the ln of 2. And fair enough. So then lastly here, if you plug in 0 there, what you can do, you get the ln of 1. That's really saying the following. If you have the ln of 1, it's saying what power do you put on e to get 1? Well, that's 0. So here you go. There is the limit as t goes to 0. Lastly, they're asking us to find the derivative. So let's go to a new page and do that. Actually, I'll make it a little bigger. So the derivative of this thing is you find the derivative of each component. All right. So I would start by thinking of this as pi minus t to the 1/2 power. Okay. Everything else would be fine. So r prime, or whatever I call this thing, gamma prime, okay, of t is equal to, well, this is going to be 1/2 pi minus t to the negative 1/2 times negative 1 by the chain rule, right? Take the derivative of the outer function, something to 1/2 power, that's 1/2 something to negative 1/2. The derivative of the inner function here is negative 1 with respect to t. The next component is the quotient rule, fortunately. If you remember how to do the derivative of this thing. So quotient rule uses the bottom times the derivative of the top. The derivative of ln2, of 2 to the t is 2 to the t ln2. And the derivative of minus 1 would be 0. Okay? That takes care of that. Minus the high function, the top function, times the derivative of the bottom, which would be 1, all over the bottom squared. And then lastly, the last component, the derivative of the ln of something is usually the derivative of that over the thing you were taking the ln of. So it's going to be 1 over t plus 1. So there it is. You can simplify a little bit, but not much happens. Okay? Sometimes people forget that. So you have a function that looks like y equals a to the x. Y prime is a to the x ln a. If you have y equals a to the u, where u is a function of x, then y prime is a to the u ln a times u prime. It's sort of like a chain rule there, right? You take the derivative of the exponent. Let's continue. All right, so I guess we'll stop with this one today. It's asking for the equation of a tangent line to a function, okay? And you're given the point. So your line, the only thing you need is to get the slope, or not the slope, but really the direction vector of the line. And you do that by taking the derivative of this thing. So the derivative of this thing would be negative sine of t, cosine t, and the derivative of e to the t is just e to the t. Okay? All right. So the only thing you might be unsure of is what was t in this case. You have to figure that out, because you want to be able to sub in the correct parameter value here to get the direction vector we want at this point of tangency. So take a look at, you know what? I made a mistake here. I made one mistake here. Well, we'll come back to that. Just to quickly comment over here, if we look at this, we look at t, and we look at this expression, we match it up, we can see e to the t in the last position, and t must have been pi over 4. So that was actually pretty easy. Now you should verify it works for some of the other values. So for example, if I put pi over 4 in the first thing, I get cosine of pi over 4. Well, that's rad 2 over 2, and I'm not surprised. I'm supposed to get that. And then I have t sine t. This is a mistake I made a minute ago. If I plug pi over 4 into that, I have pi over 4 times the sine of pi over 4. But that's pi over 4 times sine of pi over 4 is rad 2 over 2. So that's pi rad 2 over 8. So that works also. So this is definitely the value of t I'm interested in. Mistake I made a moment ago is I forgot to notice this t here. To do this derivative of the inside, you need to do a product rule. So it's going to be first, derivative of second. So it's t cosine t plus second sine t, d first, which is going to be 1, comma e to the t is its own derivative. Okay. So there you go. You just plug t equals pi over 4 into that, and you'll have your direction vector. You have the point. You can write your line. So here we go. Ready? So if I plug pi over 4 into that, this is going to be negative rad 2 over 2. That part's easy. Here I'm going to have pi over 4 times the cosine of pi over 4, which is rad 2 over 2, plus over here, the sine of pi over 4 is rad 2 over 2 times 1 doesn't do anything. And then you're going to have e to the pi over 4. Okay? So that's your direction vector. So we're ready to write our line. Our line isn't a big deal. It's x of t equals the point we want to go through, so it's this, rad 2 over 2, plus the scalar t times this piece, negative rad 2 over 2. Okay, so there it is. It's your first component. Your second component is y of t equals, all right, and that was pi rad 2 over 8 plus this whole thing times t. So pi rad 2 over 8 plus rad 2 over 2. And then lastly, z of t is equal to e to the pi over 4 plus t times e to the pi over 4. And these three things here, this is your parametric equation of your tangent line.